Compared to a lot of the objects in our solar system, the Earth's moon is a bit unusual. A new theory, published this week in the journal Nature, explains how the moon got to where it is today. Professor David Rothery from the Open University wasn't on the paper, but he took me through what Matthew Cook, the study's lead author, had done. He started by explaining what makes the moon such a space oddity.
Well, it's quite large compared to us as a planet. I mean, if you go to Mars, Mars has two tiny moons, which have probably just captured asteroids. Some of Jupiter's moons are bigger than ours, but compared to the size of Jupiter, they're still pretty tiny. So we're the only planet that's got such a large moon relative to our size.
The Earth and Moon aren't just unusual in their relative sizes, they're also different in their compositions.
They're both rocky bodies. Further out in the solar system, most solid bodies are made mostly of ice rather than mostly of rock.
Next, David took me through the current understanding of how a moon formed.
The origin which has seemed to fit ever since we got hold of samples of a moon via Apollo is that the moon has formed by a giant impact. When the planets were forming, they formed by collisions between similar sized objects. That's the final stage of planetary formation. And the last such embryo to embryo collision to affect the Earth was the moon forming impact. And some of the debris from that collision went into orbit about the Earth and coalesced there to form the moon.
This giant impact theory explains some of the moon's features.
The giant impact theory works because if you hit the Earth and blast a lot of the Earth's outer part into orbit around the Earth, that can form the moon. That's fine. That explains why the moon and the Earth are so similar in terms of their isotopes.
But it doesn't explain everything.
What was hard to explain for the orbital people was the angular momentum of the Earth-Moon system. That's how fast the Earth and the Moon are spinning, and the energy, the angular momentum carried by the Moon's orbital motion, and the inclination of the Moon's orbit, and the relatively low obliquity of the Earth. That's the angle at which its axis is tilted. The Earth's axis is tilted by 23 degrees. That's why we get seasons. That's a fairly small tilt.
The previous model has difficulties in explaining the Earth and Moon's angular momentum, the slope of the Moon's orbit relative to the Earth, and how the Earth is tilted. This new model solves these problems by proposing a very energetic early Earth.
The new model that Matthew Cook and colleagues have published starts with an impact into a fast spinning Earth that's got a very high obliquity. Its axis is tilted at about 70 degrees relative to the normal to its orbital plane, and spinning with a period of 2 or 3 hours. That's a day that's only about a tenth of the current day length, spinning so fast and highly tilted. If you hit that with an impactor that can produce a moon-forming impact, that's a lot of debris in orbit around the Earth that will coalesce to form the moon. You can then evolve into the present state of things.
Once we've got our fast-spinning Earth and our collision, what happens next?
The debris that you fling into orbit about any planet that you've hit is going to be concentrated into the equatorial plane of that fast-spinning planet. And then it coalesces to form a moon about this fast-spinning, very young Earth. And then what you have to track in your modelling is how angular momentum is transferred from the fast-spinning planet to the newly formed moon, and you've got interactions with the sun as well. So you've got 3 bodies to consider while the Earth is going around the sun, and its tilt on its axis is evolving, and while the moon's orbit is evolving as well. And you've got to model how the energy is transferred from spin of the Earth to the moon's orbital motion and out to the sun and so on.
And after you've modelled all of that...
But if you have this highly tilted Earth that's subject to a moon-forming impact and track what will happen, you can get towards the present-day situation. That's the Earth with its axis only with an obliquity of only 23 degrees.
It seems that a large collision and a fast-spinning early Earth are what you need to get the Moon, the Earth and the seasons we see today. That was Professor David Rothery commenting on the model published this week in Nature. The study's lead author was Matthew Cook from the Carl Sagan Center at the SETI Institute.